Okay, happy Thursday. Let's go and get started. Today we're going to look at a thing called condition objects or condition variables. And these are another synchronization mechanism, but let's hold off on that. We'll get to that in a second. So first off, a review of locks. A lock is an object, and you acquire it. If you try to acquire it and it's already acquired by somebody else, another thread, then this blocks. Now you can set it so it doesn't block and it returns false, returns true, and it acquires and so forth. But in this case, where we just say my lock acquire, it'll block and wait. So that means if it's already acquired, it'll block. It's up to us to then wrap our critical section in that. Or remember, you could use a with block. You'd say with my lock, colon, and then indent the critical section underneath that, and it would be acquired and released automatically. But this is the basics of how locks work. Now, we also had semaphores, and semaphores look very similar. That you create the semaphore object, you acquire it, and you release it. But there are some key distinctions between those. Even though looking at these two things, they look almost identical. You create the object, you use the acquire method, you do something inside of there, you use the release method, same thing on semaphores. But the main differences between those is that a lock object can only be released by the thread that acquired it. So that the thread that acquired that lock has to be the one that releases it. Semaphores can be released by the thread that acquired it or a different one. It doesn't matter. It could be one or the other. Locks will also block if they're unable to be acquired, and semaphores only block on an acquire if the semaphore's value is equal to 0. In other words, if you have a binary semaphore and it starts off with 1, then it behaves a lot like a lock that can be unlocked by the thread that locked it or another thread. But if I have a semaphore value that's greater than 1 initially, like 2, then that means it can be acquired twice before blocks start happening on acquire, and it would have to be released twice to put it back to the state of 2. So those differences make semaphores really, you can do anything with a semaphore that you could do with a lock, but that little bit of extra power, that little bit of extra capability of being able to have a thread other than the one that acquired it release it, and the little bit of extra ability to have it have a value that counts down to 0 before it blocks. That can also make them a little more flexible, but we also have to be a little more careful with them because there's a little more complexity there that we have to think through. But they give us the ability to do things we couldn't do with locks. So semaphores can do everything that locks can do. Locks are a little more limited than semaphores. Now that brings us to what we're going to look at today. And what we're going to look at today is another kind of synchronization object, synchronization mechanism called a condition object. And to understand the motivation behind condition objects, let's start off with that kind of a buffer class. And let's say we're making this buffer, and a buffer does what buffers do. It kind of buffers information temporarily, and you feed information in, and the buffer fills up, and you take information out, and it goes down. So think of it kind of like a list of things that can grow, like a queue. So when you're running a program and you have a series of events going into the event queue of that window, that application, they're filled up by the operating system, they're pulled out by the application, or the keyboard buffer on your computer system. You type keys in, they go into the buffer, the application or the operating system pulls them out of that buffer. And that's a pretty common kind of thing to do. Same thing when you're watching something on Netflix. It has to buffer. It says buffering, and it fills up that buffer of video data that's being filled up by the network process that's getting the data for the next frames and next frames. And then it's being exhausted by the thing that's actually playing the video. So there's a buffer in between, so you have a nice smooth playback. Even though the network might go faster sometimes and slower other times and get behind on other times. And if that buffer ever gets to be empty, that's when you get that thing where it's like buffering. You have to wait for it. So this is a pretty common type of thing. And there really are two kinds of ways to interact with a buffer. You put things in, you place items into the buffer, and you take things out of the buffer with take. So we have our little pseudocode here has a place method, has a take method. And that buffer internally stores the items that come in and puts them into the buffer. And generally, we might think of that buffer, you could think of it as having this infinite size, but in practice, it can't have an infinite size. It has to have some fixed size storage array inside of there, at least a maximum size that it would grow to. All right, and keep in mind that place and take might be called concurrently or executed concurrently, with one process putting things into the buffer, another process pulling things out. Now, here's where we come up with a need for this condition object. So if we look at the way that the buffer works, so we have some kind of array, we have a count that's keeping track of how many items are in there, and then we say, well, since I have two items accessing the buffer, one to put things in, one to pull things out, and they're both, for example, accessing this shared count variable, and we know that the place would do count plus plus, we know take would do count minus minus, so we have two different threads, potentially, two different processes accessing something that's shared. The buffer array may be shared, the count may be shared between these, and it might overlap execution when we try to run those. So the problem with that being, obviously, that just like we had with this is kind of like the ornamental garden problem with a shared count. One adding, one taking away, that could get corrupted, and we'd have a value that says, hey, there's 7 things in the buffer and there's nothing in the buffer, or something along those lines. And if we're not careful with how we're accessing this array, we're accessing that concurrently. Something could be adding something in while something's taking something out. That could get corrupted potentially in some way too. So we need to be exceptionally careful with how we access that. And the idea might be, well, let's add a lock. So we add this lock to our buffer class. And then inside of place, we say, well, while we're placing things, let's lock everybody else out. So we'll lock the buffer. And when we take things, we'll lock the buffer. So that's going to ensure that we have mutual exclusion on that. That this has a lock around it. That has the same lock around it. So if we try to place and take at the same time, one will always be paused while the other one completes. Now, and that'll work, except for the concept of this buffer having a bounding size, a maximum size that we want it to be. So if we want to bound the buffer size to prevent it from overflowing or underflowing, now we might have an issue that arises. So let's look. So let's say we added to this class this max items attribute. And let's say we just want at most 10 items to be stored in there. So we have a buffer that will fill up, and once it fills up to 10 items, then we need it to not allow any more to come in. In other words, pause when we try to do a place. And we also want to bound it on underflow, meaning when it gets down to 0 items and we try to do a take, it needs to pause the take process. And so this is the kind of thing that happens a lot, that you'd want to, if you try to get a keyboard key and there's none in the buffer, it blocks and waits for a key to come in. And this happens in programming languages, like you have a C program and you call getChar. If there is a character, it gives it to you. If there's not, it blocks and waits. So these are the kinds of things we want. Now the problem here, maybe you can see that. Do you see a problem with the way this code is written? And the problem that you might notice here would be that with this place and with this take, that we've locked the lock and then we entered our loop to wait here. So we locked the door and now we're waiting inside of this spin lock here. So in other words, we're stuck inside this loop. In other words, if the buffer filled up, I lock the door and don't let anybody else in, and now I'm stuck here waiting for it to be emptied, and it never will be, because for this to pull one out, it needs to get in and use that lock, so this will lock up the entire thing. So in other words, there are a couple problems here, actually. The loops are also busy wait loops. This is running and consuming resources while it's waiting. It's just an infinite loop spinning there. That could be fixed with semaphores, but the bigger problem is that if we block to wait, either here or here, then we're holding onto the lock while we block. So the entire thing will lock up when the buffer is either empty or full. So what we need to do is a way to release that lock while we're waiting. Now, you could try something like this, where you, with the lock, you release it, you enter your while loop, and then you reacquire it. But that is actually not a solution either. That this might make sense. Like you might think, okay, well, I'll release the lock, I'll enter my wait, and then I'll reacquire, and then I'll continue on. But the problem is now I have an acquire here that if I had two things trying to place at the same time, and they're running concurrently, so two different processes feeding data into the buffer, then notice we have both of them waiting here. That max items will go to 0. They'll both continue on. They'll both try to acquire a lock, and then one of them will have acquired the lock here. The other one will be stuck there. And now that we could go to max items, that place happens, that one finishes, the other one continues on, and now we've gone off the end of that array. We've gone past max items because we're not in that loop anymore. So does that fix it? The answer is no. And what we really need is a different kind of mechanism for this. We could hack together something using a sequence of locks or semaphores or something like that, but we want something that's going to block while waiting, but also release the lock while we're waiting. So if we think about how that's needs to work, that brings us to this idea of a condition object. And what condition objects are is they work a lot like locks, but they have a few special features. And those special features are that condition objects can unlock while waiting on some condition. In other words, unlock while waiting for the buffer space to be available, or unlock while waiting for the buffer to become have things put into it. And then they can also notify other threads whenever that condition occurs. So when some action happens that would cause that condition to occur, then we can proceed. All right, so let's take a look at the pseudocode for that. And so here's some pseudocode that goes along with that. So you'll notice we have this, and again, this is not valid Python. This is just pseudocode. But here's what we do. We make, instead of a lock, we make a condition object. And now that condition object, we put it in a with block. And hold on a second, there's I need to fix the code here. So I'm going to pause this for just a second. I'll be right back. Okay, so we're back to the code. I just had a typo in there. I had one extra thing and I had to take out. All right, so basically what we're doing is we come in, we say with the condition variable, and notice that that's inside of it. So we've actually acquired the lock on that, but we can still do a wait inside of it. And that temporarily releases the lock while we're waiting here, while the count is equal to max items. So the only way we'll ever get past this loop is that max items is no longer what count is equal to. So when count has to be less than max items for us to continue. And since this is inside of a lock, where the only way it will get released is if it's either available and it didn't wait, or it waited and then was notified by one of the other processes. The only place that could be notified is down here when something was just removed from the buffer. And so this is the basic idea. Note this is pseudocode. This is not Python. Let's look at how to do this in Python. So to do this in Python, it works a lot like the other objects, except we use threading.condition to make a condition object. We store that in a variable. We acquire, we release, or you could use it with block, just like you can with locks or semaphores. But then it has a couple other things here. Wait, which causes it to block but release the lock while it's blocked. Notify, which says, hey, find some other thread that's waiting on that. If there is one that's waiting on it, unblock it, release that lock. And there's another one called notify all, which can notify all of the things that are waiting. And generally the way you would implement that is you put it inside of a while loop like this. So even if you notify all and they all wake up and try to continue, only one of them will get the lock because it's still a lock, and only one at a time can have that. So when it hits that, wakes them up and they all go to continue on, it still is only one of them acquiring that lock. But the idea here is this could be used to have, rather than notifying just one thing that's waiting, notify a group of things that are waiting. Now, before we do that, before I say we're done today, let's actually write the code for that. So give me a second to switch the screen over so you can see the code that I'm going to write. And what I'm going to do is I'm just going to quickly throw together some code. So let me start up a Python shell here. Give me just a second. And let me resize this so you can see what I'm doing. Let me make sure you can see that on the screen here. Oh, well, first I got to switch this over. Give me a second. All right, so there's my programming window. Let me make sure it all fits on the screen. All right, that looks pretty good. So what I'm going to do is I'm going to go ahead and write this code quickly to illustrate kind of this with that buffer object. So first off, I'm going to import threading. I'm going to import time. And I'm going to import random because we're going to do a random time delay, which is why I have time and random there. And I'm going to make my class, we're going to call it buffer. And basically, let's make the constructor. So def underscore underscore init underscore underscore. I'll just put self here. All right, so now we're ready. So that's the special method. That's the constructor. Let's actually create a buffer in there. And I'm going to do this in a kind of Pythonic way rather than making a statically allocated thing. I'm just going to make the buffer a list. I'm going to have our count variable start out at 0. And for right now, let's go ahead and do it the way we did in that pseudocode. So let's say max items equal, and we'll allow it to only have up to 10 items in there. Now, right now, I'm not going to make a condition variable or anything like that right now. Let's go ahead and write the rest of the code. So we'll make the methods. We'll come back and we'll add the condition later on. So def place. Here's our place method. We're going to place an item. So I'm going to pass an item in to be placed. And essentially what this is just going to do is we're just going to say self.buffer. So that buffer list, we're going to add to the end of that our item. So we're going to stick that item on the end of the list. We're going to increase the count. So self.count plus equal 1. All right, so that's adding an item to the buffer. Now let's add one for take. So to take something from this, we'll do self. And here I'm just going to say, let's do it this way. Let's say item equal, and I'm going to do self.buffer.pop. And I'm going to pop the thing off the beginning of the list. So it's going to get the thing from the front of the list. So that's getting the item, and we're going to return it. But before we return that, we need to decrement our count. Don't forget that. So self.count minus equal 1. All right, so there's our basic buffer. And notice it doesn't have any protection right now. I'm not using max items for anything to check on anything. I'm also, in this case, I'm not making sure I'm not taking from a buffer that's empty. So really, I probably ought to put some kind of a check around this. But before I do put any of those checks and add the condition variable, let's actually go ahead and write the code to test this. So I'm going to make a couple threads. And actually, to make those threads, I'm just going to make a function. I'm going to say produce, okay, let's call this produce 100. And that's just going to produce 100 items. So let's do for I in range, not range, range 100. And what am I going to do each time? I'm just going to call item or buffer. Actually, we need a buffer. We'll make the buffer instance in a second, but I'm going to do, yeah, let's actually go and make the buffer instance. So let's say buffer equal buffer. All right, so this is calling the class. The class is like a blueprint. We're making one of these objects. And just to make it clear, let's call it this, my buffer. Now in produce 100, I'm going to say my buffer dot. Now this is producing. So producing is putting them in there. So this is going to be place. And I'm just going to put the number I in there. So I'm just going to put that integers that are generated in that for loop. So 0 through 99, those are going to get placed into that buffer one at a time. Now, to make it so that it doesn't do it really fast, I'm going to go ahead and add a little time.sleep in here and say time.sleep. And let's make this random. So random.uniform. And let's go 0.001. So 1,000th of a second to 0.01 hundredth of a second. So we delay a little bit, place an item, delay, place, and we do that for 100 times. Now let's do the same kind of thing for consume.
So I'm going to make another function. Let me move this down a little bit. I'm going to call this consume 100. And when I consume these, I'm going to do the same thing. I'm going to sleep a little bit, but here I'm going to do a take. And I'm going to pull that into a temporary variable I'll call value. Value equal buffer.take. So whatever came out of the buffer, I'm putting in value. And then so we can see the things that are coming out at the end of this, I'm going to put a print statement here. So let's just say print. And let's put the index here. Let's do, we'll just say item. And let's put I. So it's item number I. And then let's put the value that we found in there. So value. Value. And let's put how many are in the buffer right now. So buffer, or let's just say count. And that's going to be, what did I call it? My buffer. Dot, what did I call it? Count. Okay, so we produce 100 things going into the buffer. At the same time, 100 things are going to come out of the buffer. And each time we pull one out, we're going to say, hey, I got item number 1 or 0. It was value 0. It was here's how many things are in the buffer right now. Okay, so what I'm going to do is let's make those into threads. So let's say thread 1 or T1 equal threading dot thread target equal, in this case, produce 100. So there's thread 1. Thread 2 is going to be the same thing, but thread 2, threading.thread, target equal, consume 100. Now let's start both those threads. So T1.start, T2.start. And now let's join them. So T1.join. So waiting for them to finish, so T2.join. And now let's just print out a thing at the end here that says done. Now, back to our code up here. One of the problems we might have with this code, well, let's run this and see what happens. Buffer condition.py, whatever, we can call it whatever we want. And you notice that it looks like this worked pretty well. That we went through, every item went in, every item came out, the count kind of grew. But notice we didn't take into account the max of numbers. The count actually grew pretty large there for a while. It went from all the way up to, what, 73, I think was the largest that it went up to. So the buffer grew pretty large there. But you'll notice it looks like it preserved the order pretty well. We went from 0 all the way up through everything there. And that's to be expected because we're putting things in at a different end, but we didn't guard this. So there is the possibility that we could consume something before, or the buffer could become empty. And to illustrate that, let's change the timing a little bit on these. So the timing down here, let's make it so it takes a little bit longer to produce than it does to consume. So in other words, let's make this go from 0.0, or here, let's do 0.01 to 0.02. So the producer is now slower than the consumer. And let's run that. And notice it immediately failed. We tried to take something from an empty list and it told us that. So it popped from empty list. And notice how quickly that happened. So again, this is why testing things with concurrency, let's put that back again. 0.01 there. Let's do 0.001 here. And that's why testing this, there it didn't work when I had it like I did the first time. If I run that again, didn't work. Run it again, didn't work. Run it again, works. And again, that's the problem with concurrency, is that running it and testing it and saying, hey, this looked like it worked great. Why run it again? As soon as you have concurrency, you have non-determinism, and you end up potentially having problems. So I just ran it and it worked great. Now let's add our bounding for that buffer, and then let's protect those things a little bit. So let's add the bounding for our buffer. So to bound that buffer, we want to make sure it doesn't ever get more than 10 items in it. So to do that on place, what I want to do here is I want to say, okay, while I'm trying to place something, here I want to wait. So what we might say here is, for example, while count, so self.count, is equal to self.max items, then here we're going to wait. And what I'm going to do when I wait, and actually I use curly braces, I don't want to do that. To wait, I'm just going to do a time.sleep here. So time.sleep of a really small amount of time there. So in other words, we're going to sleep for a thousandth of a second if we're forced to wait. Now we're going to do the same thing in take, that we don't want to be able to take an item if the buffer is empty. So if self.count is equal to 0, then we're going to sit here and we're going to wait. But we still have the problem with this, and we might run this. This might look like it's going to work. And notice the buffer filled up. The buffer is staying full, and then it finally gets exhausted at the end. So you'll notice that everything came through okay. And we might think, well, you know, this is great. Everything's working fine. The buffer kind of filled up. You can see it fill up here, and then it stayed full the entire time. Take place, take place, take place. And then eventually it exhausted back down to 0, and every item came through. But this code is still not correct. You might run this and it might look correct. You might get the right answer. We might run it multiple times. But again, we're modifying that count variable and changing that buffer. And we're doing that concurrently. This and this are happening concurrently. So there's a concurrent update there that could manifest itself. And we can end up with a count that's either over what it should be or under what it should be. We could end up with everything came through and the count was wrong at the end. And these being concurrent makes it difficult. And again, one of the things that we might notice about this, these two things here, is before, remember how it failed when we made this, the timing on this longer on the produce? Now you'll notice that's not a problem. It doesn't crash anymore because we can't pull out of an empty buffer. So I can actually have the produce take longer, or let's make the consume take longer this time. Or actually, let's make the produce take way longer here. Let's do 0.1 second to 0.2 seconds. Let's do that. And now you'll notice the count never really gets off 0 because the producer is so slow that the consumer is always able to keep up. But again, this code is, even though this is going to work right and probably give us the right answer, this code is not right because we have a concurrent update there. And again, that's why we have this concurrency classes, so you can recognize those things. So we need, here, let's do a 0.01, 0.02. All right, so let's make these the same again. And one of the things that you may have asked is like, well, why when these match does the consumer always seem to, the producer always seem to get ahead? And that's because we have this print going on here. This print statement is actually slowing down this loop considerably on this end. And that's why the producer is able to stay ahead of the consumer, even if we lower these times here. That console I/O, especially in idle through Windows, is exceptionally slow and is yielding processor here while it's waiting for the stuff to go through the operating system to show up in the little window. So that's why this one is significantly slower than if we had to print both of these, then it would more even out. Now, anyway, last thing I want to do here is, since these are not correct up here, we need to have something to lock those out. So let's add a lock to start with. So let's say self dot, we'll just call it lock, equal threading.lock. So let's create a lock object. And then here, let's acquire it. So let's say self.lock.acquire, like that. And then at the end of this, let's do self.lock.release. So we acquire the lock, we update the buffer, and then we release the lock. And let's do the same thing in the take. Lock, dot acquire, and right before we return, release. All right, so that might make sense, but when we run that, you'll notice it immediately locked up. And the reason being that if the buffer is empty and we try to take from it, it hits this while loop, and now we have the lock, and we're waiting here for something to change. The count is never going to change because we're stuck there. And if I run that again, locks up again, locks up again, again. Oh, it ran a few times that time. I don't know if you can see that or not, but it ran a couple of iterations and then locked up. I don't know if you can see that. Hold on, let me move that up where you can see it a little better. Oh, the buffer filled up that time and locked up. So we need to release that lock while we're waiting. And really, there are problems with that. For example, if we say, well, why don't we just move the acquire to after the while loop? Well, that might be an idea that we could try. So while we're affecting the buffer, touching the buffer, doing that. The problem with that is if we had two, let's say we have two things placing, they could both check this max items at the same time and say, hey, we're not at the max yet. So we go past the while loop, and then one of them goes in, increments the count, is now max items, and then the other one gets scheduled and goes in, and now we're over the maximum number of items. So this check of max items needs to be while we have the lock, but we can't have this as a while loop because now we're stuck here. So let's just switch this over to using a condition variable here. So here, instead of lock, I'm going to call it condition. And really, you could still call it lock, but to make it clear, I'm going to change this. We just change that to condition to use a condition object. Now, again, the difference between condition objects is rather than doing this sleep here, I can actually do self.condition.wait. And wait blocks, not only blocks, it means yields control back to the another thing, but so now it's in a waiting state, and the only way it can get awakened is if something else notifies it. So there's that. So what I'm going to do down here in this one, I'm going to do the same thing. Self.condition.notify or .wait. Wait there. Now we have a wait in each of those where we had those while loops before. And that's good because now they're both going to block. They're not going to be consuming CPU resources. But now we need a way to wake them up. So in other words, what we need to do now is before we release that lock, or actually that needs to be condition now. Let's make this condition dot acquire, condition dot release, and down here, condition, and up here, condition. All right, so now we're everything's good, except we don't have a notify. So in other words, right before I release this lock, I need to do a self.condition.notify or a notify all, either one. And what that notify is going to do, that's going to tell the other thing that's waiting to go ahead and try again. And if it goes through this while loop and this condition is still false, it'll hit the wait again. So even if you had multiple ones of these trying to place at the same time, and then one of them is going to get to go, one of them is going to have to end up waiting. Because wait, when I do a notify, only one of them will be awakened and then continue on. So let's do the notify at the bottom of this code too, right here. And let's run that and see what it does. And now you'll notice it'll work. And now it's actually a correct solution, that we're guaranteed to have all of those things go through. The buffer can still fill up, but it won't ever overflow. And our count will never be wrong. We'll never, because we're only ever going to be in this code or this code, just like with a lock. And so the easiest way to think about a condition variable is think about it like or a condition object, is to think about it like a lock that can temporarily relinquish its hold on the lock while it's sleeping and waiting. And then notify, think of that as, hey, wake up one of the people that's sleeping, and they'll wake up, and then they'll say, oh, it's my turn to go and use the lock now, one at a time. So if we think about this like again, we've used this porta potty analogy several times in here, but you basically go to use the bathroom, and if the door's locked, you take a nap on the ground outside. And when somebody is done using the porta potty, they come out and notifies like, hey, wake up somebody that's waiting for me. Wake up anybody who's sleeping on the ground outside the porta potty. A little bit weird, but if you've been to a music festival, maybe not all that far removed from reality. Hey, buddy, wake up. You can use the bathroom now. Oh, it's my turn. And they go in and they lock it. And then when they come out, they do a notify. Now, if you do a notify and nobody's waiting, that's fine. So notify if nobody is waiting, you say, hey, look around. Nobody's here. Like, the bathroom's available. Hey, wake up. If nobody's there, there's nobody to wake up. So this devolves to a null operation or an empty operation if nobody's waiting. So now we have condition variables, and that'll work regardless of the speed or the timing of those. So if I make the producer, here, let's make the producer much slower. It'll still work and it will not underflow. And again, that's the whole idea of buffers. You have something being produced at a different rate than it's being consumed. It's a synchronization mechanism to make sure that we're not trying to take things that haven't been produced or put things in that overrun that buffer. And again, when you're watching Netflix or YouTube video, this kind of thing is happening all the time. And now you notice we did have the buffer tick up once there. There's another one that went into the buffer. So I'm going to keep playing with the number here until we start getting some things where the buffer fills up, gets emptied. So let's do that. Let's leave that one at 0.1 and let's put this one at 0.05. See what that does. Okay, there we have the buffer filling up, emptying down. That's a little more accurate view of that buffer, but you'll notice we always get all the values coming through. Okay, so that's it for this lecture. Let me go back to the lecture just temporarily here. And hopefully those of you who haven't done a lot of Python programming are kind of getting a little more familiar with how to do classes. Basically, a class is a blueprint. The constructor is always named this __net. We always put the self parameter as the first thing in every one of the methods. We don't need to put those in when we call it, only when we're creating it. And really, that's kind of like if you're used to other programming languages, like that's like the this reference that refers to this object itself, this object instance itself. And then all of the attributes we just attach to that self. In other words, attach them to that object instance. And then after you create that class, we need to make an instance. There's instance of my buffer. That's an actual object of that type. And then we can use that from that point on. And really, we could have this down here as long as the code isn't called. So this doesn't have to be up here. I'm actually going to move that down there. And there's our little bit of threading code where we start both threads, wait for them to finish, and then print out done at the end. Okay, so that's it. That's all I'm going to cover today. So let me quickly switch back to the thing. So finish up your lab 3. We are going to have another lab next class. I decided to give you guys a little break today and over the weekend. It's Thursday. I don't want to give you, well, I do want to give you another lab, but I'm going to give you guys a break. We've had pretty much a lab a day for the last few lectures, so I'm going to give you guys a break today. We will, however, have another lab next week on Tuesday. So try to finish up all of the other ones. And next class, we're going to have a lab where you're going to do some condition variable stuff to kind of simulate a factory with multiple production cells feeding into a pipeline of other things and then feeding those on and then having it come out at the end completed. So go ahead and finish up lab 3 for the rest of the time today. Relatively short lecture, only 40 minutes, but that'll give you a lot of lab time to get this finished. And then next class, we're going to have another lab. So So everybody stay safe, wash your hands, stay out of trouble. If you're stuck on stuff or have problems, send me a text message, send me an email, let me know. I'm happy to help. But you have to let me know if you're struggling with things. All right, that's it.